Okay, well, hello everybody. Thank you to the organizing committee for the invitation to present today. My name is Sam Wadsworth. I'm Chief Scientific Officer at Aspect Biosystems, and it's my pleasure today to talk about the progress we've been making in developing our portfolio of bioprinted tissue therapeutics. So our mission at Aspect is to develop these bioprinted tissue therapeutics that are allogeneic cell-containing implantable tissues that are able to restore, replace, or supplement complex biological functions that are lost in disease. And we think these are going to be the next generation of cell-based therapeutics that are able to provide a durable, functional cure for a variety of difficult-to-treat diseases. Some background on Aspect. We're a Vancouver, Canada-based company. We are well-funded. We've raised significant funds from the Government of Canada and the local province of British Columbia. We closed a Series B round earlier this year as well. We have a team of over 100 interdisciplinary scientists, engineers, therapeutic developers, all based in Vancouver. We have a strong IP portfolio, initially centered around our bioprinting platform. More recently, we have filed and have granted patents on the bioprinted tissues themselves. We have a pipeline that covers several different disease indications. Some of those disease indications that we're developing are proprietary. We have partnered programs as well. Now, our approach to bioprinting tissues encompasses several different technologies, and so the easiest way to describe our technology stack is to walk you through the process of bioprinting a tissue therapeutic. Now, that process starts by using our proprietary software to design the architecture and the composition of these bioprinted tissues. Now, importantly, we are not trying to develop bioprinted organs. So for our type 1 diabetes program, for example, we're not attempting to develop a replacement pancreas. We are developing a bioprinted tissue that contains stem cell-derived pancreatic islets that are able to replace the function of the beta cells that are lost in the disease. So it's a printed tissue therapeutic, not a printed organ. Now, on the bioprinter itself, the cells and several different liquid biomaterials are brought into contact with each other on the microfluidic printhead. That printhead is the beating heart of our bioprinting platform. Now, those materials and the cells are brought together and then cross-linked on the printhead so that we deposit a cell-loaded hydrogel fiber from the printer. And it's that hydrogel fiber containing the cells that is the building block of the bioprinted tissue therapeutics. That fiber is laid down layer by layer to build that bioprinted tissue, and we work closely with expert surgeons to investigate the most optimal ectopic implant site for these tissues, as well as optimize the surgical procedures. The microfluidic printing platform enables us to have precise control, not just over the macro architecture of the tissue, so the overall size, number of layers of the tissue, but also the microarchitecture. And so if you look at one of those cell fiber building blocks, you would see that those fibers are composed of multiple layers or shells. And so in this example, what you can see is the core of that fiber consists of the therapeutic allogeneic cells, and the biomaterial that we use for that core is optimized to encourage cell function, cell viability. Surrounding the core in shell 1 is a different biomaterial. This is a semi-permeable hydrogel that enables the free diffusion of oxygen, growth factors, insulin, glucose through the fiber to the cells in the core. But it physically prevents the influx of host immune cells to access those allogeneic cells. So that's our immune protective layer, and that enables us to deliver these tissues without having to put the patients on chronic immune suppression. Now, surrounding shell 1, we have shell 2, again, a different biomaterial. This time, we select that material so that we can optimize the interaction of the bioprinted tissue with the surrounding host. So we want to maximize vascularization around the implant and minimize fibrosis. And so importantly, we're not relying on a single biomaterial that can perform all of these functions. We select very specific biomaterials that give us these functions to maximize the function and durability of the bioprinted tissues. We're applying these bioprinted tissue therapeutics to a variety of disease indications. They fall into two different categories: metabolic, which really encompasses our liver tissue program, and also a variety of endocrine disorders, which encompasses multiple different tissue types. We think that these tissues are particularly well suited to treat endocrine disorders because the cells within these tissues are able to sense a specific stimulus and release a therapeutic hormone or factor in response to that stimulus, so that we have a very dynamic system. Endocrine organs are dynamic. They respond to stimuli and release very precise levels of hormones at precise times. And that's a very difficult thing to recreate with standard therapies. So a cell-containing bioprinted tissue that can sense and release a therapeutic factor could represent a functional cure for patients with a variety of endocrine disorders. One disorder that we're focusing on is primary adrenal insufficiency. PAI affects about 45,000 patients in the US, and it can be split into two different categories. There's congenital adrenal hyperplasia, and there's autoimmune Addison's. But in both cases, these patients have lost the function of their adrenal cortex. And the adrenal cortex plays a crucial role in regulating the body's response to stress. That stress could be physiological, such as an injury or an infection. It could be psychological, like giving a presentation at Cell and Gene meeting on the Mesa. Regardless, in all cases of stress, the hypothalamus senses stress, releases CRH, that then causes the pituitary gland to release ACTH, and it's that ACTH that goes into the circulation and stimulates the adrenal gland, the adrenal cortex specifically, to release a variety of hormones, but particularly cortisol. And cortisol is this key regulator of the body's stress response. Patients with PAI that have lost their adrenocortical function cannot respond to stress appropriately. They have a drastic reduction in the quality of life, and it can even be fatal. These patients can go into adrenal crisis. Current therapies include oral glucocorticoids like hydrocortisone, and those therapies just aren't able to recreate that dynamic regulation of cortisol that you need to function. Addison's patients in particular are desperate for a better therapy, a therapy that can get them out of bed in the morning, that can get them to function and lead a normal life. And we believe that a bioprinted adrenal tissue therapeutic could provide that functional cure that could be transformative for patients with this disease. This is some data that we've generated recently in animal models of adrenal insufficiency. And so we took cadaveric primary adrenal cells from human donors. We printed those cells into the bioprinted tissues, and we implanted them into mice that had been adrenalectomized. These are NSG mice. The lines on this slide track cortisol levels in the circulation over a 6-month period, at which point we terminated the study. The red lines show the levels of cortisol in adrenalectomized animals that received a cell-free tissue, so no cells. And then the blue lines show the level of cortisol in animals that received the human cell-containing tissue. You'll notice that the sham controls show very low levels of cortisol at all of the time points. The animals that received the human adrenal cells, the dotted line shows the level of baseline cortisol in the morning. And we can see that there's a consistent level of baseline cortisol that's released in these animals. The solid blue line shows the level of cortisol 20 minutes after injection with ACTH. So this models an acute stress signal. And in those animals, 20 minutes after ACTH injection, we see a robust increase in cortisol release, showing that these tissues are functional and able to respond to that ACTH stimulus. And that function goes out all the way to 6 months when we terminated the study. We retrieved the tissues from the animals at 6 months. We stained them for live dead. Live cells come out green, red cells are dead, and you can see that the majority of the adrenal cell clusters in these tissues are healthy and viable. Now, normally, your cortisol levels cycle naturally during the day. in humans, your cortisol levels peak just before you wake up in the morning, and they drop off over time during the day, and they're low in the evening. Now, mice are nocturnal, so their cortisol levels are low in the morning and high in the evening. We wanted to see whether these tissues that we implanted were able to respond to the endogenous ACTH in the animal and reproduce that diurnal rhythm of cortisol release. So we measured ACTH levels in the morning and the evening in these animals. It's low in the morning, high in the evening. That's the chart on the left-hand side of the slide. And remember, these animals are nocturnal, so that's the pattern we would expect to see. When we measure cortisol at those same time points, cortisol levels reflect the ACTH levels. So we're able to reproduce that diurnal rhythm of cortisol release. So in summary, these bioprinted human cell-containing adrenal tissues maintain function and viability in animal models of PAI for at least 6 months. They're able to respond to acute stress signals, in this case ACTH injection, but crucially they're also able to reproduce that diurnal rhythm of cortisol release. Both of those functions would be game changers for patients with primary adrenal insufficiency. We showed this data recently at the Endo conference in San Francisco. Many of the KOLs in the field were very excited about the potential for us developing a functional cure for patients with PAI. I'd just like to highlight a few of our leadership team. We've brought on some really experienced developers of combination products, particularly in the endocrine space over the last 6 to 12 months. My colleague Tim Key is here. If you see Tim, please stop him in the corridor, say hi. And I'd also like to thank our fantastic team of scientists and engineers based in Vancouver. If you're ever in town, look us up. I'd be happy to show you around. With that, thanks for your attention, and I hope you enjoy the rest of the meeting.